One of the reasons we care about faults is earthquakes. Earthquakes are vibrations of the earth caused by sudden movements along a fault. Thus, regions of the world that have a lot of faults are more likely to have a lot of earthquakes. What regions of the world have a lot of faults? Well, anywhere that's near plate boundaries. If you look at a map of the world that shows recent earthquakes, such as the USGS map shown here, where the dot symbols were used to show earthquakes, you can see that if you map out the earthquakes of the world, you pretty much are outlining the plate boundaries. For review, can you look at this map and find some of the major plates that we talked about last week, like the Nazca Plate, the South American Plate, the Cocos Plate, the Juan de Fuca Plate, the North American Plate, the Pacific Plate, etc. So earthquakes occur along faults, and faults are more common near plate boundaries. Thus, it makes total sense that Alaska and California experience a lot more earthquakes than, say, Kansas or Iowa or Virginia. The active plate boundaries of North America are along the western margin of the North American Plate. Here's a real-time map of earthquakes in California and Nevada that I downloaded several years ago. And you can see the little red squiggly marks are faults. From our discussion previously, you should be able to guess what type of faults exist here. That would be strike-slip faults. The type of faults that you expected here in the Basin and Range region, normal faults, and the type of faults you would expect up here where Juan de Fuca is subducting, reverse and thrust faults. The little squares on the diagram depict earthquakes, and you can see that earthquakes occur on faults. Furthermore, this diagram is interesting because it shows earthquakes in the last hour, the last day, and the last week. And I've actually never downloaded this map without having at least one earthquake in the last hour. That's how common earthquakes are in our region. Notably, though, most of the earthquakes on this map are very small in magnitude, 2.0 or less, and virtually most people would not feel this small of earthquake. Zooming in closer to home, we know that we live right near the San Andreas Fault System, which is a system that consists of many different right lateral strike-slip faults. Thus, we can expect to have lots of earthquakes. We've already discussed that an earthquake is the vibration of the earth produced by the sudden movement along a fault. An enormous amount of energy is released during an earthquake, and that energy radiates in all directions from the focus. The focus of the earthquake is where the actual slippage occurs. Essentially, it is the center of the earthquake. The epicenter of an earthquake is the point on the ground surface directly above the focus. So check out this diagram here from your book and notice the difference between the focus of an earthquake and the epicenter of an earthquake. When an earthquake occurs, energy radiates out from the focus in all directions in the form of seismic waves. There are three types of seismic waves: primary, secondary, and surface waves. I encourage you to review the animation from your textbook or in Mastering Geography that describes the three types of earthquake waves. I'll describe them briefly here as well, but the animation shows you a nice visual. Primary waves are the fastest waves, so those are the first to arrive at the seismograph recording station. So those were the first to be recorded on this particular seismograph. Primary waves are compressional waves, and they travel through the body of the earth. Secondary waves are the second fastest waves, so they're the second wave that we would see recorded on a seismograph. Generally, secondary waves have an up and down motion to them, and they also can travel through the body of the earth. though they cannot travel through liquids, so they don't actually go through the outer core. Surface waves are the slowest of the earthquake waves, so they're the last to arrive at the seismograph. Surface waves only travel on the surface, not through the body of the earth, and they are the largest and most destructive of the different types of earthquake waves. Notably, the primary waves are sort of like the Earth's warning signal. If you feel an odd vibration, it's time to drop before the earthquake drops you. Cover your head by getting under a table, and hold on. Hold on to whatever you are using to cover your head with so that it doesn't vibrate away from you. These first waves, these primary waves, these compressional waves, don't do a lot of damage, but they can warn us about the impending secondary and surface waves that are going to follow, which are much more destructive. Again, I encourage you to view the video in your textbook or from Mastering Geography on seismic wave motion. There are a couple ways we can go about measuring the size of an earthquake. Magnitude scales are what most of us are most familiar with. Magnitude scales measure the amount of energy released during an earthquake. The Richter magnitude scale is the most famous of these scales, in part because it's very easy to use. Interestingly, magnitude scales are logarithmic, not linear. So a 5.0 earthquake is about 32 times stronger than a 4.0 earthquake. A 6.0 earthquake would be 32 times stronger than a 5.0, or 32 times 32, which is about 1,000 times stronger than a 4.0. Similarly, a 7.0 earthquake would be 32 times 32 times 32, or roughly 32,000 times stronger than a 4.0 earthquake. Wow. So for every unit of magnitude that you go up, there's a 32-fold increase in energy. Luckily, we don't have many of these higher magnitude earthquakes each year. But there's, as you can see, millions of these smaller earthquakes. Another useful scale for discussing the size of an earthquake is earthquake intensity. Intensity scales measure the amount of shaking that occurs during an earthquake, based on the amount of damage observed. The most widely used intensity scale is the modified Mercalli intensity scale. This scale runs from 1 to 12 and, like all intensity scales, uses Roman numerals to distinguish it from a magnitude scale. As you read the table here, you can see that the definition for each number here on this intensity scale is fairly qualitative. This is how, though, that they gather evidence in terms of how much damage occurs. In fact, if you ever feel an earthquake, you can go to the USGS websites, click on earthquakes, and report what you feel and how much damage you saw. And it's through that data that they're able to make maps showing the shaking intensity of particular earthquakes. Here's a map showing shaking intensity from the 1989 Loma Prieta earthquake, the large big one here in the Bay Area. The epicenter was south of us, sort of to the east of Santa Cruz, and you can see that right around the epicenter is where the most intense shaking existed, which makes sense. And then as you go further away from the epicenter, the shaking decreased. But it didn't decrease the same everywhere. You don't have to go very far to the northeast here before you're down into a shaking intensity of 6. Whereas you can go all the way up here into San Francisco and still be at a shaking intensity of 7. So the distance you are from an earthquake does impact how much shaking you have, but there's also something else at play. Your underlying geology is very important. Basically, if you're on solid rock, there's less shaking. And if you're on unconsolidated sediments like gravel, sands, and especially muds, the shaking is amplified and you'll have more shaking. We'll continue to talk about this further in the next few slides. Here's the modified Mercalli intensity scale map for the 1906 San Francisco earthquake. Here's where the epicenter was, just offshore of San Francisco. But notice that the greatest amount of shaking actually occurred up here by Santa Rosa. So location is important. The closer locations typically have more shaking, but underlying geology also plays a role. There's a lot of unconsolidated sediment up here from the tidal sloughs, and then also the way the mountains are arranged here, it turns out that the vibrations were amplified as they bounced back and forth between these two small mountain ranges. We're not going to focus on that part of it, but I do want you to focus on the underlying geology and whether you're on solid rock or unconsolidated sediment. Let's go back to the Loma Prieta earthquake. During the 1989 Loma Prieta earthquake, the Bay Bridge, part of it collapsed, as well as the Cypress Freeway structure in the East Bay. Well, the portion of the freeway that collapsed was a portion that was anchored in unconsolidated sediments, as opposed to solid rock. Unconsolidated sediments, like sands, muds, and gravels, shake a lot more than solid rock. We can see that here in this figure from your textbook that shows seismograms that are recorded in 3 different geological settings: solid rock, sand, and muds. The seismograph recording on the solid rock, there was very little shaking. The sands and gravels, a little bit more shaking. And the unconsolidated soft muds, a whole lot of shaking. And this region of the freeway structure that was anchored into these softer muds was where the freeway collapsed. Let's take a bigger look, though, and think about where else might we have unconsolidated muds as our underlying geology here in the Bay Area. Do you live in the sandy regions of the Sunset part of San Francisco or the Richmond? Or maybe in the muddy areas like the Financial District, the Marina District, the Mission, the Dog Patch, down here to South San Francisco, San Mateo, Belmont, San Carlos, Redwood City, East Palo Alto, Menlo Park, Palo Alto, etc. All around the bay here, we have unconsolidated mud. If you live in this region, you should expect some considerable shaking during the next earthquake. In addition to the shaking intensity, locally we also have to worry about liquefaction. Be sure to review your textbook's discussion of liquefaction and all the other earthquake hazards that your textbook discusses. This is important. Liquefaction is one hazard, and it occurs in areas with saturated sediment. That means, for instance, all the flatlands around the San Francisco Bay where there's saturated muds. When the ground shakes, these saturated sediments behave like a liquid. Pipes float up and break, and houses and other buildings sink. You can check your neighborhood's risk for liquefaction on the zoomable map on the USGS website. I encourage you to check out this website here. Notice all of Foster City and Redwood Shores are in the high liquefaction danger area. If we zoom in, you can actually go neighborhood by neighborhood and find where you live. I live right here, very close to a very high red area for liquefaction, but I'm actually in the moderate region. Where are you? Because we live near local faults, because we're near a plate boundary, we know that we need to be prepared for the next big one. Are you prepared? And we also now understand that our underlying geology puts us at risk as well. If we live on unconsolidated sediments, which many people do around the Bay Area, we're at risk for more shaking and liquefaction. 10 years ago, geologists told us that there was a 62% chance of a 6.7 or greater magnitude earthquake in the Bay Area. Now that probability has risen to 72%. And every year that we don't have an earthquake, that probability continues to rise. Are you prepared?